recording of the lecture. That at least is going to work right now.
Oh, I might be wrong, but yesterday when I looked at the YouTube video, I don't think the voice recorded. Like the video, like I could see all the writing, but I'm pretty sure, like I turned the volume up and I couldn't hear you talking.
Okay.
Just
Well,
wanted to let you know.
I'm sorry about that. Okay, I'll check that out. Okay. So, where were we? We were in section 1.1 of the book. We defined metric spaces. We haven't proved anything about metric spaces. Are we going to prove anything today? I don't think so. But we're going to state some results without proof today. But first we need a definition so that we can do something in metric spaces. So we're going to talk about what it means for a sequence to converge in a metric space. Now, tau has a different convention than we're used to. Tau indexes his sequences in the superscript. So his sequences, they look like x to the parentheses n. I mean, you have to use parentheses so it doesn't look like a power. And the reason he's putting it in the superscript is because he wants to use the subscript for components of vectors. So, okay. The other thing tau does is he starts his sequences not at 0 or 1, but at some arbitrary number m. I mean, it's all equivalent, but it's just a different convention, okay? So this right here that I've written is our standard sequence in this book, okay? Now, the definition is that, oh, and I should say, in X, X is going to be our set. We might say in XD, okay? But I will put the D here in a minute. Converges to X with respect to the metric D. Okay, that's what we're defining. And now, metric is just a generalized way to talk about distances. So our definition is exactly the same as the one you know, except we're going to put in the new metric. So remember your definition of convergence. It means for every epsilon greater than 0, there is a capital N. Now, since we started our sequence at little m, we want this capital N to be at least little m, such that now we want to say that the distance between the points in our sequence and x is small. So the distance between the nth term of our sequence and x is less than epsilon for all n at least capital N. Okay. So what has changed from last semester? Well, our notation for sequences has changed. Now we're going to say with respect to a metric, and instead of the absolute value metric there, we've got an arbitrary metric D.
So if you wanted to show a very specific metric in a problem, let's say, you just literally plug in the xn and the x into the definition of that metric, where it says d xn comma x less than epsilon.
Mm-hmm. Mm-hmm. And we'll do an example here in a minute. Let me first, just so we're clear, oops. So if this holds, we're going to write the limit thing. So we write that the limit as n goes to infinity of the sequence xn is equal to x. Okay, what you'll notice about this statement is that it does not say what metric we're using. And that's sort of a problem. Okay, the limit depends on, it might depend on the metric. We'll get to some examples here in a second. So the metric has to be understood. Okay. So if you see a limit statement, it needs to have been said what metric you're in. Otherwise, it doesn't make any sense. Okay, let's do an example.
Somebody asked a question.
Oh, thank you. Ah, wow, Madeline has skipped way ahead. Yeah, we're going to get to that result. Let's do our example first, and then we'll go to Madeline's observation here. Example, let's let our sequence be defined by, let's say, 1 over n and 1 over n squared. This is a sequence in R2. Okay, so it's a sequence in the plane. Now, if you plotted this sequence, what would you see? You'd see 1, 1, and then you'd see 1/2, 1/4, and then you'd see 1/3, 1/9, and so on. So you're tracing out this parabola, okay? And you're going towards the origin, right? So this is a sequence of points that really ought to converge to the origin. So now let's check. So our claim is that in our various metrics, this should converge to the origin. So we're going to do 3 different computations here. We're going to look at every metric separately. So with respect to the L2 distance, the limit of the sequence is the origin. Okay, how do we prove that? Well, we do our computation. So we compute what is the distance in the L2. That's, remember, the Euclidean Pythagorean metric, between 1 over n squared, and 0, 0. Okay. Well, that is the square root of 1 over n all squared plus 1 over n squared all squared, which is the square root of 1 over n squared plus 1 over n to the 4th. We want this distance to be going to 0, so we want an upper bound. Okay, any suggestions for an upper bound on this distance?
Is that less than or equal to if you were to just 1 over n plus 1 over n?
We could do 1 over n plus 1 over n, or we could just take this. This is the bigger term. The 1 over n squared is the bigger term. And so we could just double that, square root of 2 over n squared. So 1 over n to the 4th is less than or equal to 1 over n squared. Okay, now that clearly goes to 0. Okay, and now we're going to skip some steps because we know how to do this, right? Because those distances are going to 0, for any epsilon, there would be a capital N that we could choose so that we could make this distance less than epsilon. Okay? So we have shown that with respect to the L2 metric, the limit is the origin. Okay? Now let's just look at the other two metrics that we've defined on R2. With respect to the L1 metric, what would our distance be? We'd be looking at 1 over n squared to the origin. Oops. That would be equal to, remember the L1 is the sum of the absolute value differences. So it would be the absolute value of 1 over n plus the absolute value of 1 over n squared. Okay, and then we could say 1 over n is the bigger one. So we're less than or equal to 2 over n. And the absolute value doesn't matter. These go to 0. So we do indeed converge to the origin. Okay.
Someone wants to know if n still
Oh.
means natural numbers.
Oh. Yeah, Brett. The let me do this in green over here. That is true. That is true in any math class, I would venture to guess. Now, is 0 in that set or not? I haven't bothered to look yet to see what tau does. I would hope that 0 is now suddenly a natural number, whereas in the fall it wasn't, according to our book, okay? But we haven't used this bold n yet. We haven't talked about the natural numbers. We've been talking about capital N's. So a capital non-bold N. Okay, let's go with respect to the infinity norm. This, remember, is the maximum of the absolute value differences. Okay, that maximum will be 1 over n. Again, we're going to 0, so we do converge to the origin. Okay. So in all three metrics, we got the same answer. But the speed at which we converged did change depending on the metric. Okay, but we got the same answer. Now, let's look at another metric. So now we're going to look at the discrete metric. Remember that the discrete metric is the one that's 0 when the 2 points are the same, and 1 if they're different, okay? So in the discrete metric, what's the distance between 1 over n and 1 over n squared? I think Daniel's talking, but I think we've lost volume again.
Yeah, wow. Go ahead.
Well, I'll just write in the answer there. It's 1, okay? Because 1 over n and comma 1 over n squared is never the origin. It gets close to the origin. Well, it gets close in the first 3 metrics to the origin. But in the discrete metric, it never even gets close. It's always 1 unit of distance away. So with respect to the discrete metric, the sequence does not converge. So with respect to the discrete metric, the sequence 1 over n squared does not converge. Now, Madeline has already supplied the the natural extension to this, which in the book is proposition 1.1.19. And I will just abbreviate it with respect to, oops, there's a 2 in WRT. With respect to the discrete metric, the only sequences that converge are the eventually constant sequences. So the convergent sequences are precisely the eventually constant sequences. Okay. We'll leave the proof of this as an exercise. It's also an exercise in the book. It's a good exercise to think about. Think about how you would prove this. It's really an if and only if statement. So if you do converge in the discrete metric, well, then we get to use that convergence definition. So we'll pick our epsilon to be like 1/2, and then convergence says we'll eventually be within 1/2. Well, the only way the discrete metric can be within distance 1/2 is if the distance is 0. So we have to always be distance 0. In the other direction, if we are eventually constant, well, I mean, then eventually our distances are all 0. Okay, so you could prove, you could also prove that in fact, no matter what metric, an eventually constant sequence does converge, which is reassuring, right? Okay. Another result that I'm just going to quote from the book. We proved this last semester for real numbers. In fact, let's abbreviate it because if your sequence has a limit, that limit is unique. Okay. Now, if you go and look at your notes from last semester, it's exactly the same proof, except you replace the absolute values with the metric. Okay. So you argue, well, what if it had two limits? Well, you look at the distance between those two limits. It has to be positive. That's one of the axioms of a metric. If 2 points are different, then there's a positive distance between them. And then you remember what we did is we cut that distance in half, and we said eventually we're within, half the distance of one of the limits and half of the other limit, and that can't happen by the triangle inequality. Okay? So again, if you just look at the proof from last semester, exactly the same. Oh.
Metrics that you converge, the limit is the same, or just within each metric?
Oh, I'm sorry. I need to add, yes, for each metric. Okay. So if you converge in a particular metric, then your limit is unique. Okay. We have not proved anything about changing metrics. So right now it's conceivable that we could change the metric. We could actually get different limits. Okay. But we haven't proved anything about that, and I'm not making a claim about
Is
that.
that something we'll touch on?
Probably not. Okay. Now, what do we have left that we want to do? So, I want to touch on the relations between the three popular limits for Rn. Popular metrics for Rn. So remember, these are our metrics on R to the n. So I'm talking about just n tuples of real numbers. It's a vector space if you want to think about it like that. They're the ones we just used. The L2, the L1, and the L infinity. Okay. Euclidean taxicab and soup norm are the word names for them. Okay, there are relations between these three. So, let me just write these as inequalities, then we'll talk about how you would prove them. The L2 metric between x and y is always a lower bound on the L1 metric, but the L1 metric can never be bigger than the square root of n times the L2 metric. Okay. Now we have one more relation between them. I'll just write that. A lower bound on the L infinity metric is 1 over the square root of n times the L2 metric. And an upper bound on the L infinity metric is the L2 metric. Okay. Now there's a lot of things to prove here. There's 4 inequalities. I'm going to copy the book and again leave this kind of as an exercise, but we should talk about how you do it. Here, the L2 and the L1 metric being, the L1 metric is an upper bound on the L2 metric. This is actually just you write out the L2 metric and you can just do some inequalities, and this is true, okay? The other easy one is the L infinity metric is less than or equal to the L2 metric. You write out what the L infinity metric is. It's the maximum absolute value difference in a coordinate. Well, that's going to be a lower bound on the L2 metric because one of the terms in the L2 metric would reduce to the difference in that coordinate. Okay. Any thoughts about the other two where we've got these square root of n's hanging around?
Wait, I just realized it's actually one string of, like it can be one
Oh.
string of inequality because the DL2 on the bottom right is the same as the top left.
Yeah.
Okay.
Yeah, for sure. For sure. So, and the important thing is that everybody's sandwiched in between everybody.
Okay.
So, what have we done? The L1 metric is sandwiched between the two L2s, and the L2 metric is sandwiched between two L1s. Do we actually have that? No, but anyway, this gets a little bit messy, and so that's why I was trying to avoid it. I think that's also what Tao was doing when he wrote his book, was trying to ignore this by making it an exercise. But where are these square roots, the square root of n's coming from? We'll talk about that briefly. It's something you've probably heard of. So I will just be reminding you that this is the Cauchy-Schwarz inequality. In the book, this is exercise 1.1.5, and it kind of walks you through how to prove it. It's not difficult. What it says is that if you sum AI, BI. So what is this? This is really the absolute value of a dot product on the left-hand side. That's at most the sum of this, well, I'll just write it. It's at most the guess we haven't defined norms, so I can't say norm. The square root of the sum of the squares of the a's and the times the square root of the sum of the squares of the b's. Okay, so this is really a fact about vectors in Rn. Okay. Now, that is where all these square root n's are coming in. You're actually taking one of these vectors to be the all one vector. Okay, so for example, if we let bi's all be 1, then on the left we'd have just the, well, sorry. If we let the bi's all be 1 and we let the ai's be, say, xi minus yi, then on the left we would have the L1 distance between x and y. And on the right, over here, we'd end up with the square root of n. And here we would end up with the L2 distance between x and y. Okay, so once you've got Cauchy-Schwarz, these inequalities follow. And Cauchy-Schwarz itself is not all that difficult to prove. And if you look at the exercise, it walks you through it. Okay, so one more result I'm not going to prove, but I will state. And it's a very reassuring result, again. And it says, with respect to these three metrics, convergence is exactly the same. Okay, so it doesn't matter which of the three metrics you're using. So this is proposition 1.1.18, equivalence of metrics. So it says, now, we've used way too many n's today. N is the index of our sequence. It's the dimension of our space. We used a capital N for where the convergence starts, and so on. So anyway, we have to switch one of them. So we're going to switch the index of our sequence from an n to a k. So the sequence x to the parentheses k, and we will start it at m and go forever. Let this be a sequence from Rn, and let x be an element of Rn. You'll notice this is going to be a classic thing throughout this course. We're not going to make a big deal out of vectors. We're not going to write them any differently from anything else. They're just points in a space. So, what is this? The kth term of our sequence, what it really is this awful looking thing. It has n components, right? That's how we would write it if we needed to talk about the components. We would say x to the k sub 1 up to x to the k sub n. Okay, what's the statement of the theorem here? The following are equivalent. One is that the sequence converges to, so now I'm just going to basically say it converges to x, but in the three different metrics. So the sequence converges to x with respect to the L2 metric. It converges to x with respect to the L1 metric, and it converges to x with respect to the L2 infinity metric. Okay. Once you've got those inequalities that follow from Cauchy-Schwarz, this proposition is not difficult to prove, it's just a little bit messy. And the key is that, you go back up to those inequalities, the key is to remember that the dimension of the space isn't changing. So when you've got these square root n's and 1 over square root n's, those aren't changing. Okay, our index of our sequence is k, not n. Okay, so those are just constants in the proof. What in the other one? Kishev points out, yes, yes, I misspoke here. I think I just got turned around in an inequality. I invite you to double check yourself. Okay? So basically where we are is that this is section 1.1. We've defined a metric space. We've looked at examples. The big 4 examples we've done are the 3 metrics on Rn, and then the discrete metric that we can put on any set. Okay, today we talked about how the three big metrics on Rn are all equivalent in the sense that convergence in one is the same as convergence in the others. What we haven't done is kind of any more exotic metric spaces, so I guess in the last minute or two that we've got left, I want to introduce a couple more metric spaces. So here's one. Let's let C01 be the set of continuous functions with domain the closed interval from 0 to 1. So with domain. Okay, so that's just a set of some objects. The objects happen to be functions, but in terms of metric spaces, we're just going to call them points. Okay. We can define what would the distance between. So I'm gonna let my functions be f and g. What would be a possible metric on this set of functions? And now I realize that I can't hear you, I don't think, right now. So let me just fill in the answer. The first answer should be a possible metric on a set of continuous functions is the discrete metric.
Somebody
Yes. So the discrete metric is always an option. That's not really exciting, but it's an option. Kishev says the maximum difference of the absolute values. Yeah, I guess we can pull off maximum because of compactness, because of closed and bounded interval, I guess is how we talked about it last semester. So we could do that. So we could look at f of x minus g of x, take the absolute value of that, and take a maximum. Okay? This actually came up kind of in a disguised context last semester when we were talking about uniform convergence of functions. Uniform convergence of functions, so let me just change this to There we go. Uniform convergence of functions, as we defined it last semester, is convergence in this metric space. Okay. So already we're seeing that as we abstract to the notion of metric space, we actually simplify, and that one notion of convergence actually just became the notion of convergence. Okay, that's an option. And let me show you that there's a third option we could do. If we want, we could just integrate the absolute value of the difference. Okay.
Well, you said that was the third one, was the first though?
The first option is always the discrete metric.
Oh,
Yep. Okay. So, I mean, I hope that's at least a slightly more interesting example of a metric space. Let me just conclude with one more. I think I can do it quickly. Let's let M by N be the set of M by N matrices over, it doesn't matter, but we'll say that their coefficients are real numbers. And then what would a metric on two matrices be? Well, again, the discrete metric is always an option. But another thing you could do, this works out to be a metric. You could set it to be the rank of their difference. Okay, so you check, if you plug in X and X, then the difference between the two matrices is the zero matrix. It has rank 0. Anything else has to be a non-zero matrix over there, so it has to have rank at least 1. Checking that the triangle inequality holds takes a little bit, you have to remember a little bit of linear algebra. Okay, so you have to think about the row span. Okay. So, it's a couple more examples of metric spaces. Friday, we will move on to section 1.2.